Hi, my name is Tyler Turner, and this is my video for Lab 4 for Physics 2. The purpose of this lab was to use a bar magnet, a conductive tube of aluminum foil, and conceptual knowledge to collect observational data, model the magnet and tube interaction computationally, and finally compare these computational predictions with the observed data. There are a few key findings that I'll go ahead and list now in the introduction. The first is that the experimental time of the experiment was 16.1 seconds, and again, this was the section of the experiment that was physical, me testing it myself. And then the second part, the simulation time, resulted in an average of 15.97 seconds, and that's obviously the simulated one with GlowScript code. And a key finding that we see after completing the lab is that the induced currents have a definitive effect on the speed of the magnet. So as long as these currents do exist, there is change on the speed. There are a few key principles that are necessary to understanding the lab. The first was Newton's second law, which states that an object's acceleration is proportional to its net force and inversely proportional to its mass. Newton's third law states that for every action, there is an equal and opposite reaction. These were both necessary for the GlowScript code. And then also we have Faraday's law, which is seen right there, and then Lenz's law, which is seen right below it. And those have to deal with current, and those were also necessary in finding our calculations. There are a few materials that we needed for the lab, the first being obviously a bar magnet, then aluminum foil, which needed to be maneuvered into a tube. We also needed a timer, a magnetometer, both of those could be like on an iPhone, obviously, then a ruler for measurements, and then access to GlowScript for the coding portion. There are two general big steps in the lab, but obviously broken into smaller parts. The first was to form a tube with the foil, set up the magnetometer, and record the average amount of time it took for the bar magnet to pass through the tube. We did this 5 times, recorded it, analyzed the video to take those precise measurements, and then wrote them down. And that's how we got the average for the first part. The second big section of the lab was the GlowScript portion. So the first step was utilizing the GlowScript code to form a simulated model using the laws and effects on speed that we just saw in the last slide. And then after that, we had to compare the results of the simulated model with the real results from the first part of the experiment and see the difference. And obviously we saw that the simulated model resulted in slightly less time. Why is this? Because of a few assumptions and potential sources of error that this slide will explain. So one key assumption that we took in this experiment was that the bar magnet's field was not affected by touch. So obviously we've learned in the course before, if you touch these magnets, free electron exchange that can change the charge and influence the magnetic field. So we assume that this did not occur. We also assumed that the simulation model accounted for all relevant external effects. For instance, the GlowScript code took into account gravity, those kinds of forces, and we assume that there are no other, major forces that could potentially change the numbers we're seeing. A few sources of error. So the first could be timing approximation and mathematical averaging, because again, this was all based off of just the eye analyzing the video and seeing when exactly the bar fell through and how long it took, and the averaging and whatnot. That is all, prone to small variation. There's also the angle of the bar release. We had to release the bar straight through the tube, so if this angle was not 100% right, that could also result in variation. And lastly, the friction within the aluminum tube could also play an effect. If the bar accidentally hit the side while within the tube, that could cause friction and slow the speed, so that's another thing that could have happened. We had two key hypothetical questions to answer after completing the lab. So the first is, what if the resistivity of the conductor were reduced as close to possible as 0, and how would the dynamics of the falling magnet change? So basically this question is saying, if there was no resistance, how would this look like? How would this change the results that we're seeing? So if there was no resistance, then it would be a very strong pull between the magnet and the foil. The magnet might not even fall through all the way. It would just stick to the foil once inside of it. So this would absolutely affect the speed and, would cause a completely different result. The second hypothetical we see is, what if the holes or slots were cut into the tube, and how would this affect the ring currents in the model? So obviously if there are holes and slots, there are going to be more openings within the tube, and this would without doubt affect the current. And then as a result, the magnetic field of the experiment would also be changed, and this could also change results. And with that, that is the end of the lab video. Thank you for watching.